23 students, all right? Should be, all right? So yes, maybe some of your friends will join later today. All right, so from last Thursday, so we already discussed a little bit about the history of uh, microprocessor, right? Of the 86 microprocessor. And then today, uh, we're going to learn, right, what is inside those microprocessor. Okay, so there are two ways of the CPU or the microprocessor process the information faster. Okay, first by increase the working frequency. Okay, as you can see that nowadays, so the PC, right, the PC using is, let's say, 3 gigahertz, right, or 4 gigahertz. Okay, so the company, let's say the Intel, okay, keep increasing, okay, the frequency because they want to make the CPU working faster. Okay, but the thing is when this CPU is I mean the frequency is increased, there is a increment in the cost of manufacturing it. So we need to pay for the higher price. Okay. One more thing is by changing. All right. There are two ways. Either you change the frequency or you change the internal architecture of the CPU. Okay. As you can see from the figure, all right, from the figure there. So that's basically the architecture of the microprocessor. So where you have the from there you can see that you have the registers, okay, and then this is connected with the ALU, which is the arithmetic logic unit. Okay. Um, it's a bit blur over here. Let me try to. Okay, you have also the bus interface unit. Okay, where this is also located your register as well. Okay, and then your flags at below of the ALU. That is also the register as well. Okay, and then these are interconnect with the buses. Okay, as I said before, the bus is like a highway, right? So you can the information transferred between these registers, okay, uh, are transferred, okay, by using the bus. Okay, and the microprocessor, okay, if we feed the information to the microprocessor, let's say from the keyboard, we key in, let's say we type A, right? And then A is going to be processed by the microprocessor. Is the way before this is they fetch it or execute it at any given time. Okay. But the thing is, if you have multiple, okay, if you have multiple information to be processed, let's say you have type A, B, C, and continuously, all right, and then you want to do the other task as well. Let's say by right now, let's say by typing on the words. Okay, you also want to open the websites. Okay, so you are doing the multitasking job. All right. So the thing is, before that, long time ago, it should wait. Okay, it should wait for a task finish first, right? Before you can do the web browsing. For example, if you're doing the word microprocessing, you only can do that. Okay, but after that, you can only browse the web. Okay, but with the pipeline technology, all right, you can do the fetching and executing at the same time. Okay, meaning that it can be done in parallel. As you can see that for the non-pipeline processor such as 85, okay, first fetch and execute, fetch and execute, meaning that if you have one command that need to be executed first before waiting for the next command to come and then do the execution. All right. For the pipeline, you can do fetching and then execute. Okay, during the execution, the fetching, the second fetch comes, all right, and then do the execution of second fetching, and then the third fetching can come. All right. So that's how the pipeline technology works. So the fetching and execution can be done, okay, in parallel. Okay, so that's the meaning of the pipeline technology. Okay, so the way the 86 is doing the splitting, okay, or doing the pipelining, okay, is the execution of the EU execution unit where you have the registers there, okay, and the bus interface unit. So they're separated into the two sections. We can call this is the change of the architecture, right? If you look back here, okay, so you have the bus interface unit over here, okay. You have bus interface unit over there, okay, and then this is you have the execution unit. So this is your execution unit. Okay, so it is separated, okay, between those, but before it is combined, okay, execution and bus interface unit is combined, so that's why the pipelining technology wasn't possible. But when you do the separation, now it is possible to do that. Okay, so the thing is the BIU, all right, BIU is used to do certain function, all right. So BIU is used to access memory and peripherals, okay, while the EU executes instructions previously fetched, okay. So some information is stored, okay, is stored in the memory, and also some information obtained, okay, from the peripherals. Let's say your keyboard, okay, or your mouse, okay, that's the peripherals. For the memory, okay, memory is inside the your computer as well, okay. So it stores the information that you previously write, okay, that you previously wrote there, and then this BIU is traveling, okay, traveling to the bus, find the specific address where is that information, and then call that, and then that information needs to be fetched into the CPU, okay. So BIU works together with EU, all right. So BIU from here and then go to the memory, and then from memory travel back, okay, travel back, and then fits the EU, okay. So that's how it works. Okay, so the thing is VIU must always, okay, starts first, all right. So that's only it can work, okay. So VIU keeps ahead of EU, so the VIU of the 86 processor has a buffer, okay, or queue. Okay, so the buffer size is set as 4 bytes, okay, long in 88 and 6 bytes in 86. So in 86, it has a longer buffer, okay. So whenever you have the longer buffer, it means that the command that can be queued up, okay. Let's say the queue, all right, the queue can be longer. Okay, so the pipelining, as you looked before, so it has two stages, which is fetch and execute. Okay, so in more powerful computers, okay, if you have a larger frequency and so on, it can have many stages, okay. So, but basically, what you need to know is fetch and execute. Okay, if an instruction, okay, takes too long, meaning that you queue too long, right? The queue is filled to capacity, okay, and then the buses will sit idle, okay. So meaning that you know that okay, when the buffer is too long, maybe you do the so many multitasking tasks, right? So you add up to the queue, right? Until the queue is full, all right? So when the queue is full, then for example, so this is the information, all right? This is queue up information, okay? So let's say, okay, this is already full, okay? So before waiting to be executed, okay, to the EU. Okay, this is your BIU. BIU keep feeding the information over here. Okay, it keep feeding the information over here. Why my slide just gone? Let me reshare again. Okay, so this is okay where the BIU was. Okay, so BIU comes to that. Okay, so meaning that when the queue is full, so BIU cannot anymore do the job. Alright, so it will just sit idle. Okay, in some circumstances, all right, the microprocessor must flush out the queue. Okay, sometimes some information you don't really need, so it's not important. So you want to flush out the queue, right? So this queue must be flushed. Okay, this queue must be flushed. So when a jump instruction is executed, PIU starts to fetch the information from new location in the memory, and information fetched previously is discarded. Okay, so how to flush the queue? So this queue can be flushed by using a jump instruction. Okay, so the EU, okay, must wait until BIU fetches the new instruction. Okay, so this is called as a branch penalty, okay, in the computer science. Okay, if you keep doing the flushing so on, all right, so mean that too much jumping, okay, this will reduce, okay, the efficiency of a program. Okay, all right, so that's the pipelining technology, so how it works. Okay, so let's move to the register. Okay, so you know that the register, okay, stores the information temporarily. Okay, so it is inside your CPU, so it is like your memory. Okay, register is like memory, so you keep it, okay, but in memory you can store it for a long time, but in register, because there are limited amount of registers inside the CPU, So it is used to store information temporarily. Okay. So it is 1 or 2 bytes of data to be processed. Okay. And then we have the address of the data. Okay. So the general purpose register, okay, in the 86 processor can be accessed, okay, as either 16-bit or 8-bit register. So you have 16-bit or 8-bit register. And then you have other registers as well, which can be accessed only at the full 16-bit. Okay, we will look after this. What are those type of registers? Okay, so the data types, okay, can be either 8 or 16 bits, okay. To access the 12 bits data, okay, so you must use 16-bit register, okay. You cannot use 8-bit because you won't fit your data, okay. But the most significant bit, okay, of the bit will be 0, okay. You set the most significant bit of those 4 bits set to be 0. Okay, these are the register. Okay, so you have, okay, you assume that it is like a block. Okay, so it is like a block. So you have there okay, this is the 8-bit register over here. Okay, this is the 16-bit one. Okay, so these are two types of registers. Okay, you see that the amount of spaces for the 16-bit register is double. Okay, it's double from that. Okay, we have couple of names for these registers. Okay, so we have AX, okay, which we use regularly. AX, okay, BX, okay. This is a base addressing register. Okay, you will learn what is that, a base addressing register. Okay, and CX. Okay, CX is a counter, okay, in a loop operation. Okay, and DX points the data in the input or output operation. Okay, and X usually stands for 16-bit. Okay, how about for 8-bit? Okay, so for 8-bit, it can be separated into two. Either it's low, okay, or high. Okay, so AX, for example, AX is 16-bit register, AL is 8-bit register, and also AX is the 8-bit register as well. Okay, so AX comprises of AL and also AH. Okay, the first 8-bit and the first 8-bit is AL and the later 8-bit is AH. Okay, so this table summarize, okay, those registers. Okay, okay, so what we have over there, right? What we have over there is that for the general purpose register, we use AX, BX, CX, and DX. Okay, so that's for 16-bit. For 8-bit, we have H and L of that A, B, C, and D. Okay, we have AH, AL, BH, PL, CH, CL, DH, and DL. Okay, and then you have pointer. So pointer is defined, okay, by name of SP and BP. Okay, SP is stack pointer and BP is base pointer. And you have also index. Okay, index is 16-bit. And you have register name of SI and DI. and you have the segment register. Okay, so this segment register you have CS, DS, SS, and DS. And for the instruction register, these all are 16 bits. Okay, other than the general purpose, you have all of those are 16 bit. Okay, so instruction register, the name is IP. Okay, you have the instruction pointer. Okay, and then last one you have flag. Okay, flag name is actually okay defined by FR. Okay, FR, the flag register. Okay, so as I mentioned before, the general registers can be accessed as the full 16 bit or as a high byte or the low byte. Okay, so either of those three. Okay, so the CPU, okay, so we will look into how we going to perform, okay, some function with this register, okay. So the CPU can work only in binary in very high speed, okay. It is tedious and slow for humans to deal with 0 and 1 in order to program the computer, okay. So if the language if we are using consider 0 and 1 only, okay, it will take longer time, then it will consume so much spaces. So this 0 and 1 is called the machine language. Okay. So early computer only coded in this 0 and 1. So that's why you see a very huge computer, okay, like the size of a factory. Okay. Because whenever the information, all right, whenever information is stored in 0 and 1, so it takes a longer time, okay, to complete a task. After that, the assembly language was developed. Okay, so this provides mnemonic for making code. Okay, so mnemonic is the codes or abbreviation that are relatively easy to remember. Okay, so the assembly language is referred to low-level language, right? So as you have right now, you have C++, Java, and so on, right? So that's considered as high-level language, right? So the low-level language is the language that you use to communicate with the CPU. Okay. You notice that when you turn on a computer, so you have the BIOS, right? So the BIOS, okay, was programmed using the assembly language because it is a basic, okay, input-output system. Meaning that you want to make sure your keyboard, mouse working. Okay. Firstly, once you start the computer, when you press the button on the PC, right? You want your PC, okay, to turn on the screen. Okay. Your keyboard is working and your mouse is working. Okay. So how do we instruct that? Okay. So that's by using the assembly language. Okay. So this assembly language must be translated into the machine code by a program called as assembler. Okay. Okay, so we have an assembler to assemble those code. Okay, like not like other what we call other language. So when we write the code and then we want to execute, okay, the execution, okay, is what we call for the other high level language. But for the assembly language, we call it as the assembler. Okay, so that the difference between high level language and low level language. Okay. Right, to program in the assembly language, so the programmer must know, okay, the number of registers and their size, okay, as well as the other details of the CPU. Okay, but the most important is to know the register, what type of register that you want to use. Okay, so I just mentioned, so we have C sharp, right, or C++, basics, right? So these are all the high level languages. Okay, because the programmer does not have to be concerned with the internal CPU details. So you are designing the software, all right? The software works on the high level. It's inside the Windows, okay, not before the Windows. Okay, so that's the high level language. Okay, so compared to previously, so the assembly language, so we want to do the, we want to execute that, we call that as the assembler. Okay, for high level, we use a compiler. Okay, we use the compiler to solve to execute the code that we wrote. Okay, give me a minute. Okay. All right. So there are multiple assemblers available for to translate the 86 uh, assembly language. All right. So one of the commonly used assembler is Microsoft. Okay, MASM, Microsoft Assembly. Right. So this is developed by the Microsoft. Okay, and then we want to do the debugging. All right. So this is, you can do that with the Microsoft Windows. Okay. Um, all right. So how about taking a break? So for 10 minutes, okay, we will continue after this. Okay, let's take a break for 10 minutes. Okay, welcome back. All right. Um, Sorry, I think I should. I was skipping one of the basics introduction to this microprocessor that I believe that this one should be taught to you first. Okay, especially regarding the basics of the digital numbers. All right, because the one uh, that we're talking right now is more on the structure of the computer. All right. Okay, so basically last week I already touched about the history of the microprocessor. Okay, so today we should talk about this. All right. Okay, so first you will learn, all right, about the conversion of numbers. All right, and then the conversion of numbers is from base 2, base 10, or base 16. All right, and doing the addition and subtraction. Okay, and then you will also learn what is the how to perform the addition or subtraction using this two's complements, right? How the logic operations works, okay, and the logic gates, okay. You need to know what is the difference between RAM and ROM, okay, and then we will look into the structure of the microprocessor after that. Okay. Okay, so we have number system. Okay, so normally we have 10, right? Because it's replicating our fingers, right? Fingers, we have 10 fingers, so we have base 10 system, right? So, so it is human base, called a human base, okay, which is called the 10 is the decimal, okay, decimal number, okay? And then computers use the base 2, which is 0 and 1, okay? So in the base 10, we have from 0 to 9, okay, not from 1 to 10, okay, so from 0 to 9, okay, so in base 2, we have 0 and 1, okay, so this is commonly referred as bit, okay, so 0 is 1 bit and then 1 is another 1 bit, okay, so the binary system used in the computers because of 0 and 1 represent the two voltage level of on and off. So your voltage is going, if you switch on or switch off only, right? So the signal that we feed into the computer is just this signal, right? It's on off. So that's why the computer must work according to this, right? So if there is no signal, it's 0. If there is a signal, it's 1. Okay, it's switching 0 and 1 0. So it must be done quite fast. Okay. So if you consider a giga frequency, means that you have uh, less than 1 over 1 over minus 12 second. Okay, so that's very quick. Okay, so to convert the decimal to binary, okay, we want to divide the decimal number by 2, okay, repeatedly until the quotient is 0. Okay, as you can look there, okay, as you can look there, so we have 25, okay, base 10. Okay, we want to convert that to the to binary. Okay, so 25 we always divide by 2. Okay, so whenever you have divide by 2, so you have 12 and then you have one as remainder, right? So because you have uh 24, right? So you will have remainder of 1, okay, and then you divide again, so you obtain 12, right? So 12 divided by 2, 6. There's no remainder, you put as 0. 6 divided by 2, 0. Okay. 6 divided by 2, 3 divided by 2, you have a remainder of 1. Okay. 1 divided by 2, of course, it will be 0, but you have a remainder of 1. Okay. So the way you read it is from the most significant bit, okay, from the lowest part. Okay, so 110001. Okay, 110001 base 2. Okay, so that's how you do the conversion from base 10 to base 2. Okay, should be easy, right? So everyone could understand how to do that.
Okay, doctor.
All right. Okay, we want now. So now we have from base 10 to base 2. How about from base 2 to base 10? So how do you want to convert that? So this is much easier. All right, so you consider the lowest significant bit as bit 0. So 2 to the power of 0, okay, 2 to the power of 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5. Okay, so what is 2 to 0? It's 1, right? So 1 times 1, you obtain 1. Okay, and 2 to 1 is 2, 2 times 0, it is 0. 2 to 2 is 4, so it is 4 over there. 2 to 3 is 8, 8 times 0, it is 0. 2 to 4, it is 16, so 16 times 1, it is 16. Okay, and then you have 32, right? 32 times 2 to 5 is 32. 32 times 1, it is 32. So what you obtain here, all right, so you sum up all of that, so you get 53. Okay, so your base 10 is 53. Okay, so over here, if you convert back like this one, okay, you can also get the 25. Okay, so this is 1 to 0. 1 times 0 is 0, 0, 0, and then 2 to 0, 1, 2, and 3. So this is 2 to 3, which is 8, and then 2 to 4, it is 16. 16 plus 8. Okay, 16 16 plus 8 and plus 1. Okay, so you have 1 over there. Okay, so 16 plus 8 plus 1, so you get 25. All right, so that's how you do the conversion. Okay, knowing the weight of each bit in a binary number make it simple to add them together to get the numbers of the decimal equivalent. Okay, this is another way on how you can do that. Okay, so if you want to convert to the decimal, okay, to base 10, so 11001, so you just assume, you know that, okay, this is 220, 221, 222, 223, 224, okay, so it's 16, 8, 4, 2, and 1, okay, multiply all of that, and then you get a number, and then sum all of that, so you obtain 25. So it is pretty much easier. Okay. All right, now you want to do the conversion of the decimal to binary. Okay, so if you have 39, okay, so how do you want to convert that to the binary? Okay, first you look into this, you have what is the highest digit, okay, that is possible to be to the power of 2, sorry, to the base 2 to the power of what, 5, right, is 32. Okay, so you list as 32, 32, 16, 8, 4, 2, and 1. So this is 2 to 5, okay, 2 to 4, 2 to 3, 2 to 2, 2, 1, 2, 2, 0. Okay, so 32 is the largest one. Yes. So what is left? If you minus 31 minus 32, you have 7, right? So you need to find the combination for 7. So for 16, it will be 0. 8 is 0. 4, yes, 1. 2, yes, 1. And then 1 is 1. Yes. So this total up to be 7. Okay. So you got the number, right? So it will be 1, 0, 0, 1, 1, and 1. So that's equivalently to 39. Okay. So that's another way on how do you find. Okay. How do you find the binary digit from the decimal? Okay. Before this, you did the division. Okay, and then we look into the base 16. Okay, so base 16 is called a hex, okay, or hexadecimal system. Okay, representing 16 digit. Okay, it's not from 0 to 15. Okay, it is from 0 to F. Okay, you know that the number is from 0 to 9, and after 9 you have A, B, C, D, E, and F. Okay, but in terms of decimal is 0 to 15. Okay, in binary you have 4 bits. Alright, is 0, 0, 0, 0. Okay, up to 1, 1, 1, and 1. So that's how they come out with the hex numbering. Okay, to get from 0, 0, 0 to 1, 1, and 1. So you need to consider 16 bit, okay, or 16 digit. Okay, so that's the equivalent of that. Okay, if you look for this string, how do you convert that to the hex? For example, this one. Okay, you take each 4 of that. Okay, so this 0, 1, 1, 0. So 0, 1, 1, 0 is 6 over there, and 1, 0, 0, 1, it is 9. Okay, for 0, 0, 9 is 9, and then 1, 0, 0, 0, it is 8. Okay, so 8, 9, 6, you need to put H. Okay, H is for hex. Okay, to represent a binary number as its equivalent hexadecimal number, okay, we start from the right and group 4 bits at a time. Okay, so this is I show you how to do that. Okay, so you take each of 4 of that. Okay, so 4. Okay, and then 4. Okay, and then another 4. Okay, so you need to look what is how do you know that? Okay, so this is 2, 2, 2, 0. Okay, 2, 2, 1, 2, 2, 2. Okay, 2, 2, 2, and plus 1, 4 plus 1 is 5. Okay, and then you have F because it's full 1, so of course it is F because this is 2, 2, 0, 2, 2, 1, 2, 2, 2, 2, 2, 3. So you have 8, 4, 2, and 1. Okay, you see that how you get F? So 8, 8, 4, 2, okay, and 1. So this is 15. So 15 is F. Okay, and then you have 1, 0, 0, and 1, so you obtain 9. Okay, so this is 8 and 9 over there. Okay, so you get 9F5 hex. Okay, so that's how you do the conversion. Okay, so to convert, okay, from hex to binary, okay, so you learn how to convert from binary to hex. Okay, now hex to binary. Okay, how do you do that? It is much simpler. So you just need to remember. Okay, you just separate all of that. Okay, B is, what is B? A is 10. Okay, B is 11. So you need to get 11. So 11 is 1. Okay, 8, 9, 10, 11. Okay, 8 plus 2 and plus 1, 11, right? 9 is 8 and 1, 9, and 2 is 0, 0, 1, 0. Okay, right, so you obtain that. Okay, so that's how you obtain the conversion. Okay, so this is more exercise. Okay, you can do that. Okay, you have 6B2 base 16, all right? And then this is hex. Okay, so how do you get that? Okay, as you look before, so 2 is 0, 1, 0. P is 1, 0, 1, 1. Okay, and 6 is 0, 1, 1, 0. Okay, and 9 F to D. So for F, you always know it is always 1, 1, and 1. Okay, 9 is 1, 0, 1. Okay, and 2, it is 0, 0, 1, 0. And D, so D is equivalent to what? 13, right? Right, because B is 11, C is 12, D is 13. Okay, so 13 is 1, 1, 0, 1. Okay, so that's how you get the answer. Okay, so any questions so far? You guys clear how to do the conversion? So make sure you are mastering it, all right? Because you will learn a more complicated language after this, all right? So this is the basics, right? So now we want to perform conversion from decimal to hex, okay? From decimal to hex, how we do the conversion? We'll need to look into the changing decimal to binary first, okay? So what is equivalent of binary of that? Okay, so 4, 5, all right, so it is 0, 0, 1, 0, and 1, 1, 0, and 1. Okay, so that is, okay, in terms of okay, so how you learned before, you need to divide with 2, right? So you need to divide with 2. So you know that 45, what is the highest one? Is 32, right? So it is 32. So 32 it is 5. So if you do the conversion, all right, 45, you divide with 2, all right? So you obtain 22. Okay, you have remainder of 1. Okay, 32 divide with 2, you obtain remainder as 0, you got 11. Okay, 11 divide with 2, you got remainder 1. Okay, and then you have 5. 5 divide with 2, you got still remainder of 1. Okay, and then you divide with 2, right? So it is 2 by 2, it is 0. Okay, so that's the number that you should obtain. Okay, okay, and then you have remainder of 1 there. Okay, so over there you obtain 2 and remainder of 1, and then 2 divided by 2, and then you have 1, and then you have 1 there. once you finish with that. Okay, so it is 1 0 1 1 and 0 1. Okay, so 1 0 1 1 0 1. Okay, 1 0 1 1 0 1. Okay, so you get that, and then this one you do the conversion to the hex, so you divide 4. Okay, this is will be 0 and 0. Okay, this is D. Okay, this is 2. Okay, it is 2DH. Okay, you managed to get it? So, all right, similarly for the other two example. Okay, so if you have 6 to 9, okay, 6 to 9, so you're considering it to 6, 7, 8, 9. Okay, this is 2 to 9, right? This is 2 to 9. Okay, it's not 29, it's 2 to 9. Okay, it is 2 to 9. Okay, it's 512. So 5121. So if you minus that, 629 minus 512, how many is left? Okay, you can calculate that. 629. So you have 7 and 1 and 1 7. Okay, so that's not enough. So 128 is also not enough. 64 is enough. Okay, you minus 64. So you get 3. Okay, and then 11 is 53. Okay, and 32. So 53 minus 32. So you obtain 19. Okay, 19. Okay, so you got 16, and then you have 3 left. Sorry, it's 53. Okay, 32. Sorry, it is 3 1. 2 1. Okay, 2 1. So you need to get 21. 16 plus 5. Okay, 4 and 1. Okay, so you get 1 0 0 1 1 1 0 1 0 and 1. Okay, so that's how you get the base 2 number, and then from that base 2 you need to convert to hex. Okay, so that's the way how you do that. Okay, so I hope you clear with that. Any question?
No, don't.
All right, if no question, so I think I should stop with you today with that. All right, so hopefully you have question. 'If you have any more questions, so let's end the session today here. So before that, so let's everyone turn on their camera so I can take the attendance for today. One, two, three. So we only have 12 of you are here. Any more joining? So right, so we have 20 students. All right. Okay, get ready. It's 3, 2, 1. All right. Cheers, everyone. Okay, thank you all. All right. So I see you on Thursday, right? Okay. Okay, stay safe. All right. So
Okay.
bye bye.
Okay, thank you.
Thank you, Doctor.
Terima kasih, Doktor.
Thank you, Doctor.
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 You're welcome.